Hello, everyone, and thanks for joining the AstrumDrive podcast. So, today we cannot wait to share with you some really good progress we did in the last month, in the last two sprints. And today, as usual, we are joined by the head of our physics department, and he's also leading the World Drive research. Nelson, thank you for joining. So, please go ahead, the meeting is yours.
Thank you, Ivailo. Hello, everyone. Yes, we are very excited. We did have a very interesting couple of sprints. Yes, I can wait to share with you some of the results at least. And let's begin. Let's begin with some of the stuff we're aiming for. We are. You can see there that we are studying how to include electromagnetic fields in the system. And there are several ways to do that. We were thinking about some approaches. One approach we did during this Sprint 15 was writing down energy momentum tensor that has some charge configuration, with some current, charge current that was going on in the energy momentum tensor. And then from there, see if we can couple that with our space-time, which is our specific metric in particular, and not any general type of coupling. So we did that. We did wrote down the tensor with the electromagnetic field. It was classical, of course. And what we find out is like it's not that simple. We find out that it's not a good idea. It's not the best approach. It's very difficult to find out a way to say we have a current of this type of current with this specific configuration, and then couple it with this specific space-time. So really, the best approach is the approach that most people do, I think, or now we believe is that way. It's now let's say let's ask the space-time which electromagnetic field can we couple with this conjugate. And basically that's where we're doing now. So, but during the sprint, we tried very hard to look into some configuration that it was not trivial and more interesting. Some currents. We were very excited about putting currents in the system, but well, now for at least for the moment, we're dropping this and we move to the other way of implementing this, which we did during the next sprint that we will talk to you about later. Also, during this sprint, we studied the word time, what we call the word time. What is it, the word time? This is a theoretical idea, of course, of what a question that we are asking. The question is, if you have the possibility of warping uh, in some spatial direction, for instance, Alcubierre did it in the C or the X direction. We're working on the metrics in the radial direction. Well, what if we are warping in the time direction? What is going on with that? What happens there? What are the Einstein's equations? What we're attaining are they having something that we can uh, interpret physically consistent with some specific matter? So we were working on that, and we keep working on that. And what we found is like these equations are very very messy. It's more complicated than the previous ones. And also, we found that we have a couple of freedoms. Let's say the way you can warp in time could include some kinetics in the radial direction or the angular direction. And, and you can include one of them or both. And we check both alone and both together. And we have interesting things there to say, I believe. Uh, it's very complicated, but if you include one, you see that there are some equations that are more or less familiar, I have to say, for us, for physicists. But there are some that are not familiar at all, very nonlinear. In both cases, radial and angular. But anyway, if you put both together, that's really a messy problem that I have very hard time to try to simplify. and still have, because I don't believe we finally get into a simple version of the equations. But there are a few terms there that you can identify and have nice information about some propagation maybe of the information. So it is, there are some interesting things here to say what's going on with this, at least theoretically speaking, and then we'll see where it's going to leave us. The other thing that we did is just we changed a bit. Where, guys, we are working on numerical solutions of the Einstein's equations. So we expect some behavior from these equations. Even these equations are non-linear, from the start that they should behave non-linearly, but they should behave in certain way. You have a bubble, the bubble is moving, and it's going to change accordingly to a non-linear equation. But you have some stuff used to say. So we figured out that uh, instead of writing the equations the way we were trying to solve it numerically, it was better to change to other function that is included in the previous one. It's what we call there the f function. And, and doing that gave us the right behavior that we were expecting, at least for the very basis of the physically meaningful effects in the warp drive. Very nice, and we already work on that, and we got some numerical solutions about that. It's what we call then in the next couple of tickets there. You see the case one, and we correct the case one, and we did all that, and you will see that in the next sprint, during the next sprint, we found very nice plots that we can comment a little bit. And the last thing that we did, which is not the less interesting in this during this sprint, it was to explore again, but in the view of our current metric, which modifications Van de Broek did to implement and reduce the energy amounts that the Cuvier's drive require. So, we check out that. Basically, what he did was he changed the metric, and he add a term, something in the metric, specific, like that. At the end, it contributes with more positive energy than negative energy density, and that's the point that we did. And he did that, but the drawback with this approach is like. Well, it requires that you have a really, really small. You are working in very, very small scales, and we're talking about Planck scales here. So it's not uh, it's not really yet totally quantum in the approach. I mean, but it requires these scales to work it out these amounts of energy. So at least we wanted to understand fully the principles that he was using, and to see if we can extract from there something and use in the future for us. It is something that we need to do. I mean, we need to calculate some observable quantity, let's say energy density, for instance, in our approach with our metrics, which behaves similarly in some aspects, but also differently. And that's basically what we did during this Spring 15.
Thank you very much, Nelson. So I just want to talk a little bit more about all the points you raised. So the first one is why we bother including electromagnetic field in the warp drive equations. So one of the main reasons we're currently working on the warp drive is because we want to bring it into a lab. So in order to start experimenting with the warp drive in a laboratory, we have to have certain ingredients in the warp drive equations. Those are pretty much things we can test. So for example, electromagnetic field, angular rotation, some quantum fields, a lapse function, temperature, heat dissipation. So we want to include all these ingredients into the warp drive equations, because by having them, we can start experimenting with the theory in a lab. And also, to your point, we may try to experiment with the real thing by using very strong electromagnetic fields. On the other hand, we can experiment with analogous gravity. Analogous gravity means that we can experiment with water vortexes, which create kind of event horizons. So Um, for example, um, the scientists were able to prove that there is Hawking radiation using water vortexes because we see pretty much the same behavior as event horizon. They were able to do that into electrical circuits and also in optical cables. So basically, by using these experiments with analogous gravity, we can observe what is going to happen with our equations in a lab by using including the electromagnetic force, as I said, angular rotation, and so on. So because of that, it's very important to include these ingredients in our calculations. And also, Nelson, you spoke about the time warp. It's a really exciting thing because right now the warp drive is being perceived as something uh, like travel with very high speeds to the universe. So we can hopefully travel with speed significantly faster than the speed of light. But at the same time, when we were looking at the equations, we saw that there is no limitation in which space-time direction you can travel. You can actually travel through the time. So we're not saying that we're going to build like a time machine, but we want to experiment with these equations and see where they're going to bring us to see what is going to happen. At least from what we can see right now, mathematically it's going to be correct. So it's quite exciting direction we're working on. So Nelson, by saying that, do you want to comment any of the things I said, or you want to move to sprint 16?
I think you summarized it very well. I said basically that's our motivations, and I think I can say just add something. It's like in this analogous gravity, yeah, where people uses different as physical systems to deduce some quantities that are more, let's say, familiar with general relativity effects. There is a lot of work just by doing that, and connecting these two things together is going to be also very exciting. I mean, getting the results from Einstein's equations and then looking how to translate these into some analogous gravity experiment, that's going to be quite a journey too. It's quite exciting if you can look at these experiments and see your predictions happening or not, or happening in a different way. It's the closest that we will have to the real experiments verifications, at least for the moment. That's quite exciting too. I wanted just to add that it's very exciting to do that.
It is. Thank you very much, Nelson. So let's switch to sprint 16, which was the last sprint we were able to close. Currently, we're working on sprint 17. Actually, just looking the amount of work we were able to finish it, it's just amazing that we were able to do all of that for 2 weeks. But please go ahead.
Yeah, it was an interesting spring. Appears some things appears and during the spring that we didn't expect, and so the work grew exponentially almost. But it was a nice sprint because it was a lot of work, but it was very nice. So what happens is that during the previous sprint we started working on using the lapse function as a degree of freedom in the system that we can maybe use for our purpose. As for instance, Lenz in a paper last year, he uses the some shift vector, which is more evident using shift vector than the lapse function. But we want to go with this direction, and we find out before that this lapse function presence allow us to include more interesting energy momentum tensor, which means heat dissipation, for instance. Uh, then from that point on, what we figure out is like, well, is there are a couple of ways that you can have of coupling with matter, and then can give you an interesting a contribution from the last function, which means basically, uh, in plain English, it's like we think if we have a negative lapse function, we will be able to solve some of the problems. I don't want to go into the details, but one of them is, of course, help to solve one of the problems that reach negative energy density. And in that direction, we look into articles for what is in the literature about this lapse function. And so, in principle, it seems that it's not unobservable. But it might be. And there are some works. There is a very interesting work that relates negative temperatures with negative lapse function. And that work also leads us to a even more deep, interesting article, which is a co-author of the article is Carlo Rovelli, a very important physicist. Probably you guys heard about him. He's leading in quantum gravity research. But to his this approach he did is how to differentiate the the possibility of differentiating the sign of the lapse function without changing the signature of the gravity you already have. And that can be done probably by coupling with some specific type of matter. And saying that is a lot. So what we did, which we reviewed this article and look at what we need to do to go into that direction and to check if our metrics uh, can feed on this, and we can have best concluding physics of this. We find out that yes, the answer is we can do that, but we have to do it. And doing that is what part of what we're doing during this sprint, which is now reframing our metrics in the tetrad formalism, so we might be able to write down everything in these spaces, and in this spaces is going to be more clear on how to couple with different types of matter. Although we will pay a price, is the price is low in comparison with what we obtain about how deep we can understand the coupling. It's more like a physically clear, and that's one thing. That's basically what we do. This ticket that you see there is how called how to detect anti-space-time. So what else we did? Well, let me go a bit faster because it's a long sprint. We review the code again of case one, which is what we were doing during the last spring, and we reviewed that. And also there is a, a couple of tickets there. After reviewing that, we find out that is everything correct. We're starting to generate plots that were interesting for us. What are the set of parameters that looks more interesting? We're talking about velocities, what are the time frames we're going to use, and we found very nice plots that very nice plots that looks to show the behavior that we were expecting, and other very interesting things in there. I have to say, we have regions with you can see. I think the most interesting thing I can say at the moment, maybe you can show it there, Ipailo. It's like
Yeah.
these regions of the energy density you see in there. Well, you have yes beta pressure and also F a bit lower. I think there is a plot for the density of the system. Anyway, what you see is like you have regions with positive and regions with negative contributions. And this is something interesting because these are the numerical solutions that have very nice convergence. So we have no problems so far with instabilities and so on. And the regions that we have with positive and negative are not exactly the same in the sense that you have larger or lesser contributions of this. And this is a lot to say. We need to think through this a lot, but this is very nice. Also, the last the last plot is very interesting because this is the relation between the density energy and the pressure of the system, thinking that we have a very simple fluid in the system. And that's quite interesting because it's very complicated for something that came out from a very, let's say, simple system, a simple energy momentum tensor. So here we have a lot to say, and this is part of the ingredients that we have for the next articles that we want to submit and to write.
Right,
So this
listen,
is very nice.
here I just
Yeah.
want to clarify something, which is quite interesting. So you can see that the bubble oscillates between positive and negative energy, which is really important because it may give us a way to create the bubble with positive energy, and the bubble after the creation is going to oscillate between positive and negative energy. And I just want to clarify what is negative energy. So negative energy doesn't exist in the universe in the same way in which we don't have negative temperature. So the temperature is negative in regards to a certain point. So for example, if we have temperature below the freezing point, we say that it's like negative energy. Negative temperature, but the temperature is never a negative. It is like a negative in regards to a certain point. The same things go for the negative energy. So the energy is never negative. It is negative in regards to a certain point. So if we say that if we have a region of space in space-time which has lower energy than the background energy of space-time, we have negative energy in this region. But this doesn't mean that the energy is negative. This means that in this region we have lower energy levels than the remaining uh, background of space-time. And also, this is very obvious, for example, when we talk about the Casimir effect. So the Casimir effect is probably the only way in which the humanity was able to create negative energy-like effects. So what is the Casimir effect? So we have two plates very close to each other. So they're so close that some of the waves are like larger than the distance between the plates, and as a result, we have repulsive force between them because we have between the plates lower energy than the energy around the plate. So because of that, we have repulsive force. So I just want to clarify this about the negative energy, that negative energy doesn't exist. It is negative in regards to a certain point, which in our case is the background energy level of the universe.
Yeah, and there is some work we were doing in that direction to include what is the background. I mean, I don't know if I can go that far to say the background energy of the whole universe because this is more local. But to your point is there is no reason to think of this as an absolute value. It's always relative, and so in that sense, we're thinking in that direction to see if we can get something. Yeah. It's very interesting what we are obtaining here. Yep. And okay, so all the other tickets we have then these plots, which I think are very interesting. We are we kept working on the time warp and writing down the equations, putting everything together in some files, and trying to figure out what to do with this. And we did, but still in this process of obtaining the most simplified version of this. There are a lot of relations here that is hard to follow. Also, what we did is to keep going on the electromagnetic field, and what we find out is like the following work of a previous work. I don't remember right now the author. It's this we put an electromagnetic field that at the moment is quite simple if we just leave electromagnetic field alone, and we put that together and wrote down the system of equations, and that gives us some relations that seems to point into the direction that yes, the electric field in this case, it will impact on the energy conditions directly in a meaningful way. But still, we have to work this out better because this is incomplete. Uh, but at least we figure out, yes, we can do this in this direction, and it seems to work. And basically, that's the first step we did. Also, we added angular rotation, which is we basically this came from the time warp research, which is in the time warp, as I told you, the one of the degree of freedoms. I mean, the kinetic motions that you can have is the radial direction and the angular direction. So, what not saying the same in our our metric, our spherical metric. So what we did was, okay, let's say that nothing is moving really in the radial direction for a moment, and let's say what happens if you start moving in the angular direction. What's going on with the metric? So we check on that, and then we add both. And again, when you add both, everything explodes. But before that, you see also interesting behavior, quite similar, I must say, in the shape of the equations to the time warp, but definitely different in physically. It's going to be very, very differently, very, very different. Anyway, this probably is going to leave us as room for including uh, dynamical uh, matter into the system, which is going to complicate anything. I mean, it means basically saying that it means that your density, your pressure, even your electric field, any current, charge current that you have in the system, or any coupling, even with some fermion matter, that can evolve in time. And this is, if it's evolved in time and it has its own dynamics, well, it's going to be a whole new system. But we believe this, in this way, we can add, enrich what we can put into the system from the dynamics point of view. Uh, and well, I think that's basically what we did, because I think I check out all these other tickets before. They were more or less linked together. Um, yeah, yeah, I believe so. I already told you guys about this negative temperature and negative lapse function relation. Is there, and it's there because there is a way for coupling this uh, the space-time with different types of lapse function, which is like calling anti-space-times, and this referring probably to local negative temperatures into the system, and that's what gave us the idea. Okay, maybe we can go work this out, and we can say stuff about the lapse function and how it behaves. And this is something that we're working already right now. I mean, and also preparing how to solve numerically this system, which includes heat and so on, and also working out how to write down everything in the tetrad formalism, which is going to be very, very interesting, very nice.
Awesome.
And yeah.
Really quite exciting job. All right. So, is there anything else you want to say for the for this call?
No, no. I mean, for the physics point of view, I think I said a lot. Hope you
Yeah,
guys
you did.
were able to follow a bit of what we're talking. Please, if you have any ideas, as you're having ideas. I mean, we are having a great feedback from you. I'm very excited to see even some articles, new articles, at least for me, that I've been checking out. It's been quite exciting to hear from you guys. This keep us motivated.
Yes. Well, I have to extend your gratitude, Nelson, because uh, I'm very happy to see that we have more and more people interacting with us, sharing articles, sharing ideas, because this is very useful for us. Because to your point, we keep being motivated in this way when we see that our job, the work we do is interesting for you guys. And also, we're very grateful when you share your ideas and articles. Actually, we received several articles we didn't know about, but turned to be quite important for our research. So, guys, please do interact with us. And if you like what we do, please share the video, like the video. You can support us on Patreon. And with that, let me wish to all of you to have a very nice and successful week. Thank you for listening.